Concentration calculations part 2. So this is solubility, KSP. So solubility is a practical and experimentally derived value, and it's talking about the limit of solubility. So solubility is when I have a compound that then is dissolved in water. Oftentimes we're talking about aqueous ionic compounds, so we're talking about ionic compounds and then trying to find out what's the limit of solubility. So here's an example. The KSP of barium carbonate is 5.1 times 10 to the negative 9. Calculate the solubility of barium carbonate. So the question really is asking how many grams per liter of my barium carbonate can I expect to be able to dissolve in solution? So I have to first write my dissociation reaction. So just a reminder that the KSP is always from the dissociation reaction. So I'm taking my solid and they're becoming aqueous ions. And so my KSP expression is going to be my Ba2 plus concentration times my CO3 2 minus concentration. And that is equal to 5.1 times 10 to the negative 9, because that was given. Well, when I have dissolved barium carbonate, I create as many moles per liter of barium ions as carbonate ions. So these two concentrations are going to be equal at equilibrium. I can just call them X. And that X is going to be equal to the number of moles of barium carbonate that was dissolved per liter of solution. So that's the limit. So X times X is X squared. X squared is equal to 5.1 times 10 to the negative 9th. X is equal to 7.14 times 10 to the negative 5th molar. So at the limit of solubility, the maximum number of barium ions I can dissolve in will be 7.14 times 10 to the negative 5th moles per liter. Also the same for carbonate ions. And also that is the number of moles per liter that I can get dissolved into solution. So then the question is, how many grams is that? I multiply this concentration of barium carbonate that was dissolved times its molar mass, and I get 1.4 times 10 to the negative 2nd grams per liter. That's not much at all, right? So what this is saying is that 0.014 grams in a whole liter of water is the limit of the amount of barium carbonate that I can get dissolved in water. So practically speaking, if I put more than that in, I will have precipitate still remaining at the bottom, undissolved barium carbonate at the bottom. Another example is looking at lead-2 chloride. So if I have lead-2 chloride, this is a different example because when I dissociate lead-2 chloride, I get 1 lead ion and 2 chloride ions. So I have to remember that at equilibrium, my ratio of lead to chloride ions is going to be X and 2X. That's what I have to plug into my KSP expression. So again, we write our KSP expression first, so that's lead ion concentration times the chloride ion concentration to the 2nd power, because that's my coefficient. And that is equal to the given 1.6 times 10 to the negative 5th. So I put in 2x here and x. So I have to remember that I have to put the 2x here and then square it. The whole thing, not just the x. So the quantity 2x becomes squared. So that becomes 4x squared times x. So altogether 4x cubed is equal to my KSP value, which is 1.6 times 10 to the negative 5th. I divide both sides by 4. I get x cubed is equal to 4 times 10 to the negative 6th. I take the third cube root of this, and it becomes 1.58 times 10 to the negative 2nd molar. That's my concentration of lead ions in solution. Twice that, so about 3 times 10 to the negative 2nd molar, is the concentration of chloride ions when I reach saturation. And 1.58 times 10 to the negative 2nd moles per liter is the limit of the number of moles of lead-2 chloride that can be dissolved in 1 liter of solution. So again, to find out how many grams per liter that is, I multiply it by the molar mass of lead-2 chloride to get the grams per liter of lead-2 chloride. So just a thing to remember, a general strategy, always write the KSP expression, solve for X because that will be the moles of your ionic compound, and then the moles per liter of my ionic compound times its molar mass will give me how many grams per liter of that ionic compound I'm able to dissolve.